Good day, viewers. Today I am going to talk on number system and set theory. The importance of mathematics in business economics can be highlighted by the simple fact that almost all persons who have got Nobel Prize in economics had very strong background in mathematics. Actually, John Nash, one of the pioneers of game theory, who got Nobel Prize and on whose life the well-known Oscar Prize winner film Beautiful Mind was made, was a mathematician. No work of importance draws the attention of people unless it uses sophisticated mathematics and statistics. We will now move on to number system. We all are aware of whole numbers, which are also known as natural numbers or positive integers. The learning of counting 1, 2, 3, 4 and so on starts these days in the form of pre-nursery home education. These numbers are taken as self-evident, indefinable and having the property that they can be written down in succession one after the other without end. Also, we wish to highlight the often unnoticed ordinal, that is related to order, aspect of natural numbers, which is embedded in the counting process and which is also intended to be noticed in the figure that when we move on the right, we get larger and larger numbers. Let us recall a famous quote of Kronecker, and I quote, "God made the natural numbers, all else is the work of men." The rigorous or logical development of the number system, which is far from simple, is beyond the scope of discussion here. However, the story of progressive development of the number system can be narrated, and this is what we propose to do now. After the positive integers, one must familiarize oneself with the number 0, a number with the property that when it is added to any other number, we get the same number. Note that 0 was invented in India. For more information, see Discovery of Zero, BBC India on YouTube. It is a mystical number and its use without proper understanding may lead to wrong results. As for example, one should never divide any number by 0. It is prohibited in mathematics. Some of the false results that one can arrive at if one overlooks this advice are nicely and delicately discussed in the literature. We also have negative integers, one negative integer for each positive integer. In other words, there are as many negative integers as are the positive integers. There are many uses of negative integers. One can easily see through examples the natural occurrence of negative numbers and also their use. Examples: suppose one is talking of profit and loss and if one encounters the negative profit, it may be interpreted as loss. Likewise, negative loss can be interpreted as profit. In day-to-day life, one has to consider the problem of division, as for example, distribute 100 objects into 20 equal parts and divide 2 apples among 3 persons, so on, so that it is not difficult to imagine how important are the numbers of the type p upon q, where p is an integer and q is a positive integer. These numbers are known as fractions. They are also called the rational numbers. Their decimal representations are either terminating, repeating, or have recurring cycle, as we see in the examples. 1/2 is equal to 0.5, which is same as 0.4999, so on. 1/3 is equal to 0.333, so on. And lastly, 1/7 is equal to 0.142857, which recurs infinitely often. Starting from the very early time of the development of the human civilization, the problems involving right-angled triangles and circles came into discussions in varied situations, and they had to think of numbers which are denoted by square root 2 and pi in many different situations. These are numbers that cannot be represented or put in the form p upon q. Such numbers are called irrational numbers. Their decimal representations are neither terminating nor have repeating or recurring cycle. Another such number which comes up very frequently is denoted by E. Note that the approximate values denoted by notation equal and twiddle of these numbers are square root 2 is approximately equal to 1.41421356, pi is approximately equal to 3.14159265 E is approximately equal to 2.7182818828. We should take care not to take these values as exact or equal. They are only approximate values. Also note that rational number 22 divided by 7, a value often taken as the value of pi, is only an approximate value of pi, which is correct only up to 2 decimal places after decimal point. All these numbers, including the earlier defined numbers, are called real numbers. Thus, progressively we have got familiarity with natural numbers, integers, rational numbers, and real numbers. We now move on to real line. It is very convenient to represent each real number on a line. In fact, we associate with every real number a unique point on the line. Another way, every point on the line can be associated with a unique real number. That is, we visualize the line marked with all real numbers as we see in the figure. Square of any real number is non-negative. that is, it is either positive or 0. Thus, square roots of non-negative numbers can only be found, and if we want to find square roots of negative numbers, we have to extend our number system still further from real numbers. This is done by writing and inventing the new notation I for the square root of -1. That is, square root of -1 is equal to I, or which is same as I square equal to -1. And then defining numbers a plus ib, where a and b are real numbers. These numbers are called complex numbers. The sum and multiplication of complex numbers are defined in natural way, keeping in mind that I square is equal to -1. Thus, a plus ib plus c plus id is equal to a plus c plus I times b plus d, and a plus ib into c plus id is equal to ac minus bd plus I into AD plus BC. Note that we have used that I square is equal to -1. Now, we wind up the whole story of the number system by completing the hierarchy: natural numbers, integers, rationals, reals, and now complex numbers. We shall now move on to logic and concepts and methods of proof. Though the so-called useful mathematics is created out of the practical needs, its solid foundation rests on the logical axiomatic development of the subject. The classic example is the Euclidean geometry that we all study in our schools. The rigorous mathematical development usually consists of some undefined terms, axioms or postulates, consistency and independence of the system, definitions, examples, lemmas, theorems, corollaries, and lastly applications. Mathematical statements or simply statements have definite truth value. A statement thus is either true or false. Note that mathematical statements are eternal truths. They wear different look only when you change your system, that is, when you change your axioms and or definitions. One may also say that mathematical truths are simply logical deductions of your definitions and axioms. The logic that we use has the following main aspects: 1. Negation of the statement P, which is denoted by not P. 2. The implication that P implies Q is equivalent to not Q implies not P. The method of reductio ad absurdum, which is also known as method of contradiction. In this method of proof, one arrives at some absurd or untenable statement if one assumes that what is to be proved is false. For further details about logic, one may refer to a book by R.L. Wilder entitled Introduction to Foundations of Mathematics. We in mathematics are often confronted with several statements based on the set of positive integers. Their validity cannot be established or proved by simple verification of few cases. As you can see, the following statements are valid for a large number of initial values. However, they are false statements. 1. every positive integer n is less than 10,000. 2. The formula Fn is equal to n square plus n plus 41 gives a prime number for each positive integer n. Why are these statements false? 1. Statement number 1 is false because if we take n is equal to 10,000, the statement is false. In fact, it is false except for the initial 9,999 cases. 2. The interesting formula produces primes for initial 40 values of n, that is for n equal to 0 to 39. But when you put n equal to 40, it gives a number 40 square plus 40 plus 41, which can be easily seen to be 41 square, which is not a prime number. We conclude this discussion with a simple note that proof is a serious business in mathematics. However, when we want to apply mathematics, we will not go too much into this part of mathematics here. Equations and inequalities. In economic analysis and elsewhere, one comes across different types of equations. 1. A definitional equation. 2. A behavioral equation. 3. Assertive equation. And 4. Equilibrium conditions. We shall elaborate each one after the other now. 1. A definitional equation. Example: pi is equal to r minus c. Here r is total revenue, c is total cost. Now, total profit denoted here by notation pi is by definition r minus c. Here both the quantities are identically equal and the notation is equal to 3 bars is also sometime used. The modern notation for this definitional use of equality is colon equal or def equal. Thus, each of pi equal to r minus c, pi is identically equal to r minus c, pi is equal to r minus c, or pi by definition r minus c conveys the same thing, that profit, that is pi is by definition equal to excess of revenue over cost, that is r over cost. 2. Behavioral equation. When behavior of some variable, often called dependent variable, is described in terms of some other variable, which is usually called independent variable, we refer it as behavioral equation. Example: the 3 cost functions c is equal to 80 plus q square, or c is equal to 100 plus q, or c is equal to 100 plus 25 multiplied by q. Describe the cost c in 3 different situations in terms of the quantity of output denoted by q, which is considered here as an independent variable. Note that one supplies different values of q and cost, that is c, calculated using the formula under consideration. 3. Assertive equation. Here, in certain situation, our variables are having certain value in them, and then we say that the arithmetical expression has certain value. Example: when we know in advance that x has got definite value, say 1, that is, if x is equal to 1, then this expression x plus 4 multiplied by x multiplied by x minus 4 multiplied by x minus 3 is equal to 30. And 4. Equilibrium conditions. Suppose quantity demanded is given by Q D equal to A minus B P and quantity supplied is given by Q S is equal to minus C plus D into P, where P is the profit. In economics, it is a standard assumption that market equilibrium takes place if and only if there is no excess demand, that is Q D minus Q S is equal to 0. Thus, equilibrium condition is Q D equal to Q S, wherein we are supposed to find the value of P may be called P bar, for which the corresponding values of Q D and Q S are equal to, say, Q bar. Note the different usages of the phrase equation and the appropriate meaning of the notation equality. There should not be any confusion when only the single notation equal to is used to mean so many different things. Only the context makes it clear as to what is meant in the definite situation. To avoid confusion, the other notations may also be used for safe communication. We will now move on to set theory. Note that set theory is an indispensable tool for understanding any serious part of mathematics or its applications. It is also called the language of modern mathematics. A set is simply a well-defined collection of distinct objects. These objects may be anything. Example 1. The collection of 4 integers -4, 0, 4, 3. 2. The collection of all the subjects offered in BA degree course of Delhi University. 3. The collection of all integers. All of the above collections are sets. The objects of a set are usually called elements. Membership of a set is indicated by the notation belongs to. We note that this notation is a variant of the 5th letter of Greek alphabets epsilon. Thus, if we want to say 2 is an element of the set Z, we write 2 belongs to Z and we read it as 2 belongs to Z. The notation does not belong to, stands for, is not an element of. Thus, square root 3 is not in Z is read also as square root 3 is not an element of Z or square root 3 does not belong to Z. Description of sets. Sets can be described in 2 different ways. 1. Enumeration. Here we simply list the elements of the set. When the set is infinite and there is no point of any confusion, we use the 3 dots. They convey the information for the remaining elements of the set. Example, S is equal to -4, 0, 4, 3 or Z is equal to 3 dots -4, -3, -2, -1, 0, 1, 2, 3, 4, 3 dots. Note that these 3 dots give complete information about the remaining elements. 2. Description. Example, S is equal to the set of all x in Z such that x plus 4 multiplied to x multiplied by x minus 4 multiplied by x minus 3 is equal to 0, where Z is the set of integers. Note that we have discussed earlier different types of numbers. The notations for these sets are: for the set of positive integers n, the set of integers z, the set of rational numbers q, the set of real numbers r, and the set of complex numbers c. Now, we discuss empty set and universal set. The set which contains no element is called an empty set and is denoted by the notation phi, called phi. The idea of a universal set is very important. Whenever one is talking of anything, one has to keep in mind what is the universal set under consideration. Bertrand Russell was the one who emphasized the need of universal set. He also demonstrated that if you do not specify the universal set of your situation, you may create paradoxical statements. Universal set is generally denoted by the letter u. Sometimes context make it clear as to what is your universal set under consideration. Operations on sets. 1. Union. The union of two sets A and B is denoted by A union B and is the new set consisting of all the elements which are either in A or B. Thus, A union B is equal to the set X such that X is in A or X is in B. 2. Intersection. The intersection of two sets A and B is denoted by A intersection B and is the new set consisting of elements which are both in A as well as B. Thus, A intersection B is equal to the set of X such that X is in A and X is in B. 3. A dash B or A backslash B. The set A dash B is the set of all elements of A which are not in B. In other words, A dash B which is equal to A backslash B, which is equal to the set of all X such that X is in E, but X is not in B. 4. Complement. The complement of a set A is the set of all elements of the universal set U which are not in A. Complement of a set A is denoted by A dash or U backslash A or A twiddle. Note that complement of U is phi, that is U dash is equal to phi and phi dash is equal to U. Venn diagrams. Sets are represented by Venn diagrams. Venn diagram for union. Here A is the set consisting of 1, 2, 3, 4, 5 and E, and B is the set having elements A, B, C, D, E and 5. Therefore, A union B as illustrated will be equal to 1, 2, 3, 4, 5 A, B, C, D, E. Venn diagram for intersection. Here again A is equal to 1, 2, 3, 4, 5 and E, and B is equal to A, B, C, D, E and 5. Therefore, A intersection B will be the set consisting of 5 and E. Venn diagram for complement. Here the universal set U is represented by points inside the rectangle, and the set A here is represented by points inside the circle, which is inside the rectangle. Here A dash, the complement of A, is denoted by the shaded part. Subset and equal sets. Subset. We say that set A is a subset of set B if each element of A is also an element of B. This is denoted by writing A is a subset of B. Equal sets. Two sets are equal if each element of set A is in set B and also the other way. Each element of set B is in set A. Thus, A equal to B if and only if A is a subset of B and B is a subset of A. Clearly, set consisting of elements A and B is equal to the set consisting of elements B and A, as each is a subset of the other. This means that the order in which the elements are written in a set is immaterial. Some of the important results related with these notions are: for any set A, phi is a subset of A. For any set A intersection phi is equal to phi. For any set A union phi is equal to A. And lastly, the very important De Morgan's laws, which can be read as complement of the intersection is equal to the union of complements, and 2. Complement of the union is equal to the intersection of the complements. Summary. Familiarity with the number system was very briefly developed. We of course concentrated more on real numbers, which are most useful for understanding the mathematics of economics. Logic is implicitly hidden in any statement and proof that one talks of in mathematics. We therefore gave very brief and quick bird's eye view of logic along with the concept and methods of proof, which are generally an integral part of any mathematical discussion. The phrase equations and the notation for equality were carefully discussed. The rudiments of set theory were discussed up to the point from where satisfactory understanding of relations and functions can be built up.